The fundamental theorem of calculus, part 1, states that if f is a continuous function on the closed interval a comma b, then the function g defined by g of x equal the integral from a to x f of t dt for a less than or equal to x less than or equal to b is continuous on the closed interval a comma b and differentiable on the open interval a comma b, and g prime of x equals f of x, that is, g of x is an antiderivative of f of x, and the derivative with respect to x of the integral from a to x f of t dt is f of x. For example, let f of x be the particular antiderivative of f of x equals sine of x squared, satisfying the capital F of negative root pi equals 0. Express the capital F of x as an integral. Using the fundamental theorem of calculus, we start with the capital F of x equals the integral from a to x f of t dt, but f of x is sine of x squared, and so f of t is sine of t squared. And so it is the integral from a to x sine of t squared dt, but the capital F of negative root pi is 0, and so a is negative root pi. Another example, find the derivative of g of x equal the integral from 2 to x, the square root of 1 plus t cubed dt. Then evaluate g prime of 2 and g of 2. Using the fundamental theorem of calculus, the derivative with respect to x of the integral from a to x f of t dt is f of x. The derivative is d dx, and g of x is defined to be the integral from 2 to x, the square root of 1 plus t cubed dt. The answer is f of x, and it is the square root of 1 plus x cubed, because f of t is the square root of 1 plus t cubed. This is g prime of x, and so g prime of 2 is the square root of 1 plus 2 cubed, which is square root of 9, or 3. But g of 2 is defined to be the integral from 2 to 2 when x is 2, the square root of 1 plus t cubed dt. But the integral from 2 to 2 is 0 because there's no area between 2 and 2.